Welcome to the next lecture in the series on condensed matter theory. In this video I want to talk about the linear response of a general system derived in the frequency domain. In our previous videos we have shown the linear response of an hydrogen atom, and there we looked at a two-level system. And for a two-level system we can define a basis of phi 0 and phi 1. For our two-level system we can define the Hamiltonian minus the ground state energy on a diagonal basis, which is zeros everywhere except for the energy of psi 1, it's omega 1, and E0 is the energy of psi 0. Then we had a perturbation, a time-dependent perturbation to this system that coupled state 1 and state 0 with a dipole moment, and the Hamiltonian is time-dependent, the perturbing Hamiltonian is time-dependent, a coupling strength times operator O times sine omega t. And in our previous example, we solved this system and calculated the response for a hydrogen atom, where this is the 1s and the 2p orbital, but in principle this can be any system, a spin system, any two-level system would follow this mathematical basis. The full Hamiltonian is then given by H0 plus H1 of t, and we assume that at t is equal to 0, the system is in state 0. And then we calculated what the state at time t is, and we calculated what the expectations values of O were, and with that we could define a susceptibility. So from the previous video, we know that at time t the state is in state 0 plus something linear in lambda, and then a time and frequency dependent part times state 1 plus corrections in higher order in lambda. And f of t is given by minus e omega 1, or let's say I of t is omega I of t plus I omega cosine omega t, so something that oscillates with the eigenfrequency of the system, and then something that oscillates with the driving force and a non-trivial phase between them. Omega square minus omega I square. Note that our wave function is normalized up to order lambda, so this is 1 plus O lambda square, because this one is lambda times lambda. And if you look at the solution of the Schröding equation, minus h psi t, then you find that this is 0 plus something quadratic in lambda. So indeed this wave function fulfills the Schröding equation to linear order in lambda. Then we also showed that if you now calculate the expectation value of O for this state, then this is lambda sine omega t, and then mu1 squared, and then 1 over h bar omega minus omega 1 minus h bar omega plus omega 1, such that we can define our linear susceptibility chi1 as the coupling constant squared And then the frequency dependent part, omega minus omega 1 minus 1 over h bar omega plus omega 1. Now let's see how we can generalize this to an n-level system. So we're going to take n excited states, and we have our ground state, or the state from which we started. So in total we have an n+1 level system. And our basis is given by psi 0 up to psi n. The Hamiltonian minus E0 in units of h bar is 0, omega 1, omega 2 up to omega n, and 0 everywhere else. Or in second quantization, sum I is 1 to n for n+1 states. I don't start with 0 because we subtracted the ground state energy, h bar omega I, a dagger I, ai. And the coupling between the ground state and the excited states is given as 0, mu1, mu2 up to mu n, or sum I is 1 to n mu I, a dagger I, a0 plus mu I, a dagger 0, ai. So that our states are nicely coupled to each other. Our full Hamiltonian is then given by h0 plus h1, which is time dependent, and given by a proportionality constant, the Hamiltonian O, or the operator O, sinus omega t, such that the full Hamiltonian is h0 plus h1 of t. And again we assume that at t is 0, we are in state 0. We now can derive what the wave function at time t will be in linear order in lambda, and what we have seen before here is that to linear order in lambda the state is proportional to psi 0 without an additional prefactor, and then couples to state 1. Now the coupling to state 1 and to state 2 is independent of each other because you do not change the overlap with state 0. So for n state this is just lambda, and then the sum I is 1 to n mu I complex conjugated ft omega omega I phi I plus O lambda square, similar to the solution that we have for a two-level system. That then also immediately allows us to write down what the sustainability is, when each state contributes to the expectation value of the ground of O by in linear order in lambda, either by having the bra or the cat in linear order in lambda. So this is exactly the same as we had before for one state, but now summed over all states, mu I squared 1 over h bar omega minus omega I minus h bar omega plus omega I. So we see that for an n-level system we can calculate the susceptibility by looking how each eigenstate of H0 would contribute to the sustainability, and then just summing over all states. The sustainability for each state is independent of the sustainability given by the other state. Now let's generalize this. And we can write the sustainability as an expectation value. And that has several advantages, which we will show you once we have the expectation value. So if you act with operator O on psi0, then operator O couples psi0 to psi, and that coupling constant is exactly given by the dipole moment. So O psi0 is mu I complex conjugated times psi. So that's of course part of the intensity that we want here. So if you take the inner product of O psi with itself, the norm, you will get the sum over mu I squared. Now what is still missing is the energy dependent part. And for that we can have a look at the following matrix, given by 1 over h bar omega minus H0 plus E0 minus 1 over h bar omega plus H0 minus E0. Now of course this is a number and that a matrix, what I mean with such a number is an identity matrix times that number. So this is an n by n plus 1 by n plus 1 matrix. This matrix is diagonal, because our Hamiltonian is diagonal, and the diagonal entries are just the eigenenergies of our system. So on the diagonal you find h bar omega minus omega I minus h bar omega plus omega I. Now with this we can build a susceptibility. If I take as bra and ket O psi 0, and I take then the expectation value with respect to O psi 0 of 1 over omega minus h plus E0, then we come back at exactly this expression. So our linear susceptibility as a function of frequency is psi 0 O 1 over h bar omega minus the Hamiltonian plus the ground state energy minus 1 over h bar omega plus H0 minus the ground state energy O psi 0. Now that's very nice, because we know that expectation values of operators are independent on the basis that you use. So indeed we derived this for a Hamiltonian that is diagonal, but this expectation value is actually generally valid independent if your Hamiltonian is diagonal or not. So you can write this down for any Hamiltonian and any operator O, and then just calculate this expectation value for a state, and then you have the linear susceptibility of that state. We can generalize it one step further, because in our derivation we assumed that the Hamiltonian that we use to drive the system is proportional to strength and proportional to the operator that we use to make the measurement, and then sine omega t. So for example, you look at the electric dipole in an oscillating electric field. Or you look at the magnetic dipole in magnetic field. And of course you can look at other things, operators as well. Now we can also have a look at a system where we drive with a different operator than we measure. For example, we can look at the electric dipole for a system that we drive with a magnetic field. If we do this, then we have to modify our susceptibility slightly. We know that we take the inner product between a bra and a get state, where our states are expanded to orders in lambda or orders in O, or H1 when you drive with a different operator from O. And that operator can either be on the bra or on the get side coming from your time-dependent wave function. And then you take the expectation value of O. So one of these O's is related to the measurement and one is related to how you drive the system. And for the retarded and the advanced part of the Green's function, you either have been driving and measurement or measurement and driving. You either expand the bra or the get state to linear order and the other one to zeroth order. So we have 1 over h bar omega minus h0 plus e0 h1 minus h1 1 over h bar omega plus h0 minus e0 o psi 0 for a general substitutability where your driving Hamiltonian is different from the observable that you look at. So and with that we come to a general expression for a general susceptibility for any state depending on two operators, one that is related to how you drive the system at a certain frequency and the other related to the observable that you measure, linear in the driving force. Thank you very much. We see each other later. Stay healthy.